Hello everyone, I'm George, and I'll talk a bit about internal MPI collectives and our work with XHC. So, let me give you an idea of the problem we're trying to solve here. The issue is that modern HPC nodes are very complex. They are very densely packed with cores. For example, 100 cores or more is quite common nowadays, I believe. And they have very elaborate internal topologies. For example, multiple sockets, multiple nodes, different types of caches, and stuff like that. Furthermore, not only is just one HPC node complex, each one, or rather different designs, are different. The architecture can be different, the cache coherence scheme, the cross-socket or other types of interconnects can be different, and this again adds even more complexity. So in this field, what we strive to do is to design and implement optimal MPI collective communication that works very well with very high performance across the board for all of these nodes, whether those are AMD or Intel or ARM-based chips like here in EUPEX or RISC-V in the future perhaps, or nowadays. Alright, so quick note about MPI in case someone is not familiar. It's a communication standard for parallel and distributed applications widely relied upon HPC. There are a couple of implementations of it out there, perhaps OpenMPI and 10 bits, the main ones. And collective communication, which we will be working with, is communication that essentially just involves all processes that are in the job. A couple of different patterns that exist, like broadcast, which is one rank sends to multiple others, reduce and others, which is all ranks to one rank, and then some others that all in the form of all-to-all. Let's get into our work here in EUPEX and also in previous projects like DIPSI, which is the XMEM hierarchical collectives component. It is essentially a highly optimized implementation of internode collectives in OpenMPI. It's also actually part of the upstream OpenMPI project, and will be getting released along with the V6 series, which is coming soon. I want to clarify when I say internode, because we won't specialize in those modern complex nodes without the nuances of cross-socket, cross-node communication. XHC is really designed to work only in single node scenarios. There are some ways to leverage it in multi-node jobs. I'll talk about this a bit more in future slides. Yeah, that's the design. Now, the two main pillars of its design, as the name also suggests, is that it uses hierarchical and topology-aware algorithms. I'll talk about this a bit more. And furthermore, we utilize the cross-partition memory kernel module, XPMM for short, for cross-process communication with very low overhead. This is especially useful for very large messages. Now, neither of these two main techniques or other stuff that we use is something that we personally invented. Rather, one of XHC's features is that, or contributions, that it combines a bunch of those very high performance techniques together efficiently in one component, something which wasn't necessarily as common or at all when we first started it. And of course, we've added on top a bunch of new features and optimizations stemming from our research in the area. So perhaps the juiciest part about XHC is the hierarchy. So let me say a bit more about that. First and foremost, why do we want hierarchy at all? The issue is that when you have multiple cores communicating at the same time, and especially over distance, for example, different sockets or different nodes or caches, if you don't do something smart, if you try to do it just all over the place, you end up getting congestion. So, for example, imagine here, if this is a two-socket system, supposedly, if every core on the left socket tried to communicate with a socket on the right, you would get congestion on the cross-socket interconnect. So what one can do with hierarchy, and that XHC does, is that you can partition the total set of cores into smaller, tighter, collocated groups, perform as much of the operation possible within this tight cluster, and only then will some of the ranks in that group communicate to finish the rest of the operation. So we do that in XHC, and to do that we discover the topology of the system using the hardware locality library. This exposes features like different CPU sockets, NUMA nodes, and different caches, levels of caches. For example, in this hypothetical system here, this system, we have each of those black boxes is a chiplet, and we have 8 cores in each chiplet, and those 8 cores share an L3 cache, and 2 L3 caches are in one NUMA node. The great thing about XHC here is that all this is completely user configurable. So the user can say that I care about L3 locality, or I care about NUMA, or I care about both, including socket. There's no real limit in the implementation. So let me show you some performance figures and the benefit of hierarchy. So here this is an MPI reduced benchmark, so an all-to-one all-to-one communication pattern. This is an AMD EUPEX 3rd generation system with 2 sockets and 128 cores in total. And there are 2 takeaways here. One is, of course, hierarchy is very useful. We have XHC flat, which is a non-hierarchical configuration. And then we see that the more features that the user configures that he cares about, socket locality, NUMA nodes and stuff, the better performance we can get, the lower latency we are able to achieve. So it's definitely useful to consider all of those features in the system, especially on those on very fat nodes, with a lot of cores and a lot of topology, and on more convoluted operations, more involved operations like reduce or reduce. It's not always the case that you have to configure XHC to leverage all of these features. Sometimes it's not actually beneficial. Nothing is ever so simple. But it's definitely good to have the opportunity to do it like we do here with XHC. Being able to configure it on the fly is very important. Also, I'd like to show a comparison of the performance of XHC today compared to other implementations in OpenMPI. We have tuned, which is the default implementation of collectives in OpenMPI for single node scenarios. We have the unified collective communication library from UCX, and a recent work from AMD called ACOL. This is a benchmark all reduced, so all-to-all communication pattern. ARM Neoverse N1 system with 2 cores and 160 cores in total, so quite a large system also. 2 main takeaways here, as you probably see. XHC is it's very necessary that it's able to achieve the lowest latency compared to all other components with quite a margin in many message sizes. And also, this performance is stable across the board, which can't be said, unfortunately, or fortunately, for those other components. Some of them, or most of them, are a bit erratic in their performance, and in certain message sizes they perform quite poorly. And finally, I mentioned that XHC is designed as a single node component because that's where we want to focus. But of course, it's useful to leverage it also in multi-node jobs. It wouldn't be sane to say that we only care about single node jobs. So we can do that using another component in OpenMPI, the hierarchical auto-tuned collectives component. This is essentially a component that uses different other components for the internode and the internode phase of the operation. And we can do exactly that and use XHC in the internal phase of the operation with Han, and thus leverage its performance in multi-node jobs. Here I have some preliminary results, again reduced, so this time on the Carolina HPC system with 32 nodes. We have again tuned, and Han with its default configuration, which is tuned on that internal phase, then Han with XHC. Again, two takeaways here. XHC show us promising benefit compared to the default configuration of Han, especially on those, actually mostly on those large message sizes of over a couple of hundreds of kilobytes. And also another rather fortunate result is that tuned without Han whatsoever performs much better on those lower messages. So there is some work there in other areas to be done with Han, and we are doing some work, and I believe we will be able to make improvements across the board. That's all I have for today. It was very brief. If you have any questions. Yeah.
Did you compare with real world application or
we have done some
exhibit maybe huge variety of
some applications. You asked if we performed benchmarks with real applications, right? We've done some such benchmarks in our paper some years back. Applications like Microsoft CNTK Cognitive Toolkit with CPU only, Mini AMR, which is not exactly an application, but some sort of, and PySVM also. That's the main ones I remember having. We've tested a bunch of them through the years, but those were the ones we saw interesting benefits.
Also, it should be good not, for example, to compare also the focus of analysis not using tools like Scorpio, Scala, or equivalent to monitor not the impact of communication into the performance for real world application.
Yeah. Such tools like those you mentioned that show you very exact traces, and that's something that's on my to-do list in actual applications.
Yeah.
We do use something similar for XHC itself in mostly micro benchmarks to really pinpoint performance issues and find what's going on. Yeah, but I've always wanted to take also a look at such tools, yeah, in the future. Yeah.
I appreciate you are using Carolina for the test.
Yeah.
How are you going to present the results once it's not preliminary, but once it's final? Are you going to present the results to sysadmins, and how are you going to convince them to apply Han?
Oh, yeah. Sure, that sounds like a good idea. Especially because Han is the default component in OpenMPI since version 5, which released a couple of months back, I believe. Here you can see that tuned might be better than Han, but by default it's not used at all. So if we say that Han is going to be used no matter what, compared to tuned to XHC, here I would clearly choose XHC. So if we're able to squeeze even more performance out of this arrangement, then then it's even easier to make the case, and we should do that. Yes.
So if you need help with that, yeah, contact me.
Yeah, super.